Hello everyone, welcome back to Chemical Engineering Investment channel. As you know, these days we are focusing on the subject of heat transfer operations. So in this regard, we are bringing the lecture number 10 for our valuable viewers. In our previous lectures, we have covered various aspects related to heat transfer, starting by differentiation between the thermodynamics and heat transfer, various modes of heat transfer, which are conduction, convection, and radiation. Then we studied each aspect in detail about the conduction, its laws, which is Fourier law of heat conduction. Then we moved to convection, studied its law, which is Newton's law of cooling. Then we moved to radiation, we studied the Stephen Boltzmann law and Kirchhoff's law. In our today's video, we will combine all these aspects to do or to solve a few examples. In today's course coverage, we will solve a numerical related to the radiation first, and then using the combined principles of conduction, convection, and radiation, we will solve another numerical. So basically, there are two numericals in our today's course coverage. So before going to the lecture, if you have not subscribed to the channel yet, please subscribe to the channel. Click on the bell icon to get all updates related to this channel. So we will solve our first example. Example number one is radiation effect on thermal comfort. It is a common experience to feel chilly in winter and warm in summer in our homes, even when the thermostat setting is kept the same. This is a natural phenomena. This is due to the so-called radiation effect, which results from the radiation heat exchange between our bodies and the surrounding surfaces of the wall and ceiling. This is a basic intro of our today's activity. Let's assume a person which is standing in a room and its temperature is maintained at 22 degrees centigrade all times. The inner surfaces of the walls, floors, and the ceiling of the house are observed to be an average temperature of 10 degrees centigrade in winter and 25 degrees centigrade in summer. So the person temperature and the surrounding temperature are provided to us, and the surrounding temperature for winters is 10 degrees centigrade while for summers is 25 degrees centigrade. Determine the rate of radiation heat transfer between this person and the surrounding surfaces if the exposed surface area is 1.4 square meter and the average outer surface temperature of the person is 30 degrees centigrade. So using this information, we will see the radiation heat transfer for both summer and winter seasons. As you can see, this is the overall representation that the outer surface of this person has a temperature of 30 degrees centigrade, while the exposed surface area is 1.4 square meter, and we have to calculate the radiation heat transfer. We will go to some assumptions. Number one is that the steady state operational conditions, there is no change with respect to time. Number two, we do not consider any heat transfer by convection. This is a pure radiation example. So we will not be considering the convection heat transfer phenomena in this system. The person is completely surrounded by the interior surfaces of the room. There is no other interaction with this person, and the surrounding surfaces are at a uniform temperature. So we are just simplifying our problem. Otherwise, in reality, obviously there are some different aspects which need to be considered. Going to the solution part, first thing is that the emissivity is 0.95. Now we will solve the example. We know the formula of Q radiation is epsilon phi AS Ts raised to power 4 minus T surrounding raised to power 4. This one will be for winter and this one will be for summer. So the value for emissivity is 0.95. For the Stephen Boltzmann constant, we already studied in our previous lecture, it was 5.67 into 10 raised to power minus 8. The effective surface area or the exposed surface area is 1.4. The body temperature, the outer temperature of the body is 30 degrees centigrade, and then it is converted into absolute temperature by adding 273, and the surrounding temperature is 10, again adding 273. So we get a value of heat transfer by radiation as 152 watt in case of winters. Going to the summers, we will just replace the T surroundings from 10 to 25, and the heat of conduction is 40.9 watt. This is the first example which we have solved today, which is related to the heat transfer by radiation, assuming no heat transfer by conduction or no heat transfer by convection. The heat transfer is taking place only because of the radiation. Going to the second example, again the same example, but in this case, now we are assuming that consider a person standing in a breezy room at 20 degrees centigrade. Determine the total rate of heat transfer from this person if the exposed surface area is 1.6 square meter, average outer surface is 29 degrees centigrade, and now we are introducing a new parameter, which is the convection rate or convective rate heat transfer is 6 watt per square meter per Kelvin. So now you can see that it is a combined effect of convection and radiation, while we assume no conduction in this system. So this is the statement of example number 2. Now going to the assumptions part, again steady state operations, the person is completely surrounded by the interior surfaces of the room. The surrounding surfaces are at the same temperature as the air in the room, so there is no temperature change, or you can say the system is at uniform temperature as we have seen. And the heat conduction to the floor through the feet, as you can see here, it is negligible. So we are not assuming any conduction heat transfer here. We are just focusing on the convection heat transfer, which is a bulk motion, and the radiation heat transfer, which is thermal radiations in the system. Going to the solution, first we will calculate the convective rate of heat transfer. Q convection is equal to HAS Ts minus T infinite or T surrounding temperature. So H is 6 watt per square meter per Kelvin. The exposed surface area is 1.6 square meter. Ts, which is the body temperature, is 29 minus outer temperature or the surrounding temperature 20. So we get the convective rate of heat transfer or the convection heat transfer as 86.4 watt. While for radiation, again the same formula, emissivity is 0.95. The Stephen Boltzmann constant is 5.67 into 10 raised to the power minus 8. The exposed surface area is 1.6. The outer body surface temperature is 29. The surrounding temperature is 20. Again, converting it into the absolute value by adding 273. So we get the radiation heat transfer as 81.7 watt. And then adding these two to get the total rate of heat transfer in the system. So that comes out to be 168 watts. Again, as I've said, we are not considering the conduction phenomena here because we are just ignoring it because of limited, or you can say because of our assumptions. But as you can see, once we consider all the phenomena, in the first example, we just considered the radiation heat transfer, but if we want to consider the complete phenomena, we have to add upon other aspects as well. So that's how you calculate the heat transfer rates using both convection and radiation. In first example, we just use the radiation phenomena, while in second example, we use the convection and radiation phenomena. So I hope you have understood all the aspects of this lecture. If you have any queries, feedback, suggestion, please provide it in the comment box and I would be happy to answer it. So that's it from today's lecture. Thank you so much. Please do watch, like, share the video and subscribe to the channel. Also click on the bell icon to get all updates related to this channel. Till then, it's goodbye. Stay tuned for more exciting videos on this channel.